Hello students, welcome back. We will continue to discuss basics of spectroscopy. So, what we discussed in the last two lectures is that light can behave as both wave or particle. So, we did see that during Young's experiment, light behaved as a wave. So, when light is passed through two pinholes, a diffraction pattern was obtained, which is a peculiar property of a wave. But then, during the photoelectric effect, what we saw is light behaves as a particle. Light behaves as a particle. These particles are called photons and they are associated with momentum. Now, this was a bit surprising considering that mass of light is 0. What does that mean? That photon should have a 0 momentum. If photon has 0 momentum, and how we can say it is a particle. Einstein explained this by suggesting that momentum is not 0 when a particle travels with the velocity of the light. This was very important contribution by Einstein, and for that he got a Nobel Prize. So, Young suggested that light behaves as a wave. Photoelectric effect showed that light can also behave as particle, and Einstein explained this behavior by suggesting that a particle will not have 0 momentum when it travels with the velocity of light. Now, let me explain this in detail. So, this is the equation given by Einstein for the energy of the particle. Energy is given by mc square, and that is basically equal to square root of p square c square plus m naught square c4. So, if rest mass is 0, that is what we expect for particles like photon, then this term will be 0. This term will be 0. What does that mean is, your P will be given by E by C. P will be given by E by C. Now, we know that E is equal to Sc by lambda. E is equal to Sc by lambda. What does this say is that if we calculate E by C, we will get H by lambda. We will get H by lambda. And just now I showed you that P is equal to E by C. And since E by C is equal to H by lambda, what does that mean is lambda is equal to H by P, or P is equal to H by lambda. So, now momentum is not 0, it will be given by H by lambda, and that is how particle and wave is correlated. So, these two experiments by Young and experiment done by Einstein, which is photoelectric effect, showed that light can behave as wave or particle depending on the experiment, and photons can have momentum. So, till now we are talking about light. Now, let us see what development took place on the particle front. It was de Broglie which suggested that electron, which is supposed to be a particle, can behave as a wave, and they are associated with wavelength. They are associated with wavelength. So, he thought that if light, which is a kind of wave, can behave as a particle, particle also should behave as a wave. This is basically work of his PhD theory, and you will be surprised that de Broglie got Nobel Prize for his PhD work. He also suggested that everything in the universe can behave as a wave or as particle, as a particle, and this was a big statement which was proved by Davison and Germer and Thomson. What they showed that electron can behave as a wave by doing electron diffraction experiments. And what does that mean is that electron, apart from being a particle, can behave as a wave. And de Broglie also explained, or de Broglie equation also suggests that all the microscopic particle can behave as a wave. I discussed to you in the last lecture why a baseball cannot behave as a wave, because wavelength of a baseball with some velocity is very small, whereas wavelength associated with electron is of the same order, the size of atom, and that is why electrons behave as a wave, whereas baseballs do not behave as a wave. We do not behave as a wave. The spin does not behave as a wave. So, these are the two important observations, two important findings, that both light and particle can behave as a wave and particle. Both can behave as wave or particle. The next important theory came about quantization of energy. So, I discussed how the concept of quantization of energy came. This came when people tried to explain black body radiation, atomic spectra, and heat capacity of monoatomic gas. Now, what do we mean by quantization of energy? It is very important to understand. Quantization of energy means electrons cannot have all value of energy, or electron can only have certain value of energy. So, here is a diagram of, here is a electron distribution in a hydrogen atom. So, now you can see that electrons can have energy minus 13.6. It can, electrons of hydrogen can have energy minus 13.6, minus 3.4, minus 1.5 electron volt, minus 0.9 electron volt. So, in hydrogen atom, electron can only exist with energy minus 13.6 electron volt, minus 3.4 electron volt, and 1.5 electron volt, and so on. It cannot take a value between minus 13.6 electron volt and minus 3.4 electron volt. And similarly, it cannot take value between minus 3.4 electron volt and minus 1.5 electron volt. So, electron can have certain value of energy. When electron of atom, of hydrogen atom, has energy minus 13.6 electron volt, it is said to be in a ground state. So, if it is here, then it is said to be a ground state. When it has energy minus 3.4 electron volt, it is said to be in first excited state. and electron cannot exist between these energy levels. So, it cannot exist between minus 13.6 electron volt and minus 3.4 electron volt. It can be either have minus 13.6 electron volt energy or minus 3.4 electron volt energy. That is what we mean by quantization of energy. Now, what is this, why this is important? So, suppose we bombard light on a hydrogen atom, light can give all the energy to electron or it gave none of the energy of electron. So, what does that mean? So, if I bombard a hydrogen atom with energy 10.2 electron volt or 12.01 electron volt or 12.75 electron volt, it will absorb that energy, but it will not absorb below 10.2 electron volt or suppose 11 electron volt. It will only absorb energy if photon have energy 10.2 electron volt or 12.01 electron volt. How does this 10.2 electron volt comes? So, this is the basically difference between these two energy levels. So, if electron in an hydrogen atom absorbs 10.2 electron volt energy, then it will go from ground state to first excited state, ground state to first excited state. If it absorbs energy equal to 12.01 electron volt, then it will go from ground state to second excited state. It cannot absorb energy, for example, here in between. So, they are like 5.1 electron volt. It cannot absorb that because it cannot have energy equal to minus 13.6 electron volt plus 5.1 electron volt. It cannot have that energy, and that is what we mean by quantization. So, if a light of 10.2 electron volt struck the atom, the electron will jump from ground state to first excited state. Now, let us go and try to understand quantization a bit more. In the last slide, we did see that electron absorbs light of certain energy. Now, what we are going to see that if it absorbs light of certain energy, what can happen if it tries to emit the energy. So, see here, this electron takes energy and goes to suppose excited state of 6, excited state of 6, n is equal to 6. So, it is going from n is equal to 2 energy level to n is equal to 6. Now, suppose it comes back, then what happens? So, if suppose it comes back from 6 to ground state, the energy of 410 nanometer will be emitted, or light of 410 nanometer will be emitted. If he comes back from 5 to n is equal to 2, then 434 nanometer will be emitted. If comes from 4 to your n is equal to 2, then your 486 nanometer light will be emitted, and when it comes from 3 to 2, 656 nanometer light will be emitted. So, a particular light will be emitted. What you can see here is that this all wavelength belongs to your visible region, and this is well known Balmer series. So, in Balmer series what you are doing, an electron is excited from level 2, n is equal to 2 to higher energy levels, and when it comes back to 2, when it comes back to energy level 2, then the light in the visible region will be observed. Light in the visible region will be observed. So, for absorption, for going from n is equal to 2 to n is equal to 3, n is equal to 2 to n is equal to 4, 2 to n is equal to 5, n is equal to 2 to n is equal to 6, you will need light in the visible region, light in the visible region. But suppose you are trying to go, or you are trying to make an electron of hydrogen atom in the ground state to go to higher energy levels, you will have to supply energy in UV region, not in visible region, not in visible region. So, electrons from state n is equal to 1 cannot go, or cannot, when electron is in n is equal to 1, it will not absorb visible light, and when it is coming back to n is equal to 1, it will again not emit light of visible region. So, that is what we mean by quantization of energy. So, electron can only take certain value of energy, and if you supply light which does not correspond to the difference between the energies which electron can take, there will be no transition, there can be no transition. Now, there is important difference between a macroscopic particle and an electron. Electron is a microscopic particle. Classical mechanics describes the motion of baseball, the spinning of a top, and the flight of an airplane. So, I told you that baseball cannot behave as a wave, and in that case it is classical mechanics which is going to describe the motion of a baseball. But for particles like electrons which behave as a wave, classical mechanics cannot describe its motion. It is quantum mechanics which will describe the motion of electrons and the shape of molecules such as transfers, as well as electrical conductivity and superconductivity. So, let us go and see how to describe motion of an electron. So, motion of an electron was described by Schrodinger equation. Schrodinger equation. He gave very important mathematical formulation to describe an electron trajectory, an electron trajectory. So, what is basis of a Schrodinger equation? He basically was influenced by de Broglie. He took this hypothesis that electrons behaves like a wave, and momentum of electron is related to the wavelength by equation lambda is equal to h by p. So, since electrons behave like a wave, so a wave equation of a wave can describe the trajectory of electron. So, let us think about how we can show an equation of a stationary or a standing wave which is not moving. Okay. So, this is your wave, and I have already explained what I mean by phase, and this corresponds to 0 phase. This position corresponds to 90-degree phase, this position corresponds to 150 degree, this position corresponds to 180 degree, this position corresponds to 270 degree phase, and this position corresponds to 330 degree phase, and this position corresponds to 360 degree phase. So, what is the relation between y and this phase? Y is basically vertical displacement. So, you see when theta is 0, y is 0. When theta is 90 degree, your y is maximum. Theta is 90 degree, then y is maximum. So, this wave must be defined by a sine function. So, y is a function of this phase, and that is given by a sine theta. It is given by a sine theta. So, when theta is 0, y is 0. When theta is 90 degree, y is maximum. When theta is 180, then sine 180 is 0. So, again vertical displacement is 0. So, equation of a stationary wave is function of theta, and it will be given by y theta is equal to a sine theta. Now, let us convert this theta, or try to express the equation as a function of distance. So, what you will see is, we know that one cycle is equal to 360 degree phase, and we also know that one cycle, the distance covered is lambda. Distance covered is lambda. So, basically 360 degree phase is equal to 1 lambda. So, the relationship between theta and x, which is your horizontal displacement, theta by x is equal to 2 pi by lambda. Theta by x is equal to 2 pi divided by lambda. So, you can see that theta goes to 2 pi, then x will go to lambda, and theta is given by 2 pi by lambda into x. Now, you can see if x is 0, theta is 0. So, at this position, at this point when x is equal to lambda by 2, if you put here, then 2 pi by lambda into lambda by 2, lambda cancels out, this will be pi, and you see 180 degree. When x is equal to lambda, then what will happen? 2 pi by lambda into lambda. So, theta is equal to 2 pi. Theta is equal to 2 pi. So, the relation between theta and x is theta by x is equal to 2 pi by lambda, which tells you that theta is equal to 2 pi by lambda into x. And when you put in this equation, when you plug in this equation, what you will get is yx is equal to a sine 2 pi x by lambda, a sine 2 pi x by lambda. Now, here you see this equation is, this term is function of x, and so now we are writing y as a function of x, y as a function of x. So, first we described how to write y as a function of theta. Now, we described how to write y as a function of x. Till now we have looked at what will be the equation of wave which is standing or which is stationary. But suppose if wave travels in positive x direction with velocity v, then what you expect, that distance travelled by the wave in the x direction will be v into t, v into t. In that case, your y, which is vertical displacement, will be given by a sine 2 pi x by lambda minus vt by lambda, vt by lambda, x by lambda minus vt by lambda. Now, you see this vt, velocity into time, is your distance. So, basically this is x by lambda minus another distance vt by lambda. So, now y is a function of x and t, y is a function of x and t, and v by lambda is equal to frequency. v by lambda is equal to frequency. So, y as a function of x and t will be given by a sin 2 pi x by lambda minus frequency multiplied by t. So, both are x by lambda is unitless and frequency into time is unitless. Now, we want to know how this vertical displacement, which is y, changes with x. So, how this amplitude changes with x. So, this is the same equation taken from earlier slide. If I differentiate y with respect to x, what I am going to get is a multiplied by, we know that differential of sin x with respect to x will be minus cos x, alright, and here it is sin 2 pi x by lambda minus nu t. So, what I am going to get is minus a into cos 2 pi x by lambda minus nu t, frequency multiplied by time. And then we need to differentiate this term which is with sine, and that will be equal to 2x by lambda since t is constant. See, since t is constant, here we are assuming that it is, that time is constant, and in that case this will not change when we differentiate with respect to x. So, minus a 2 pi by lambda. So, differential of this 2 pi x by lambda minus nu into t will be equal to 2 pi by lambda, 2 pi by lambda. Okay. If I differentiate again with respect to x, what I am going to get is minus a as like this. For cos, I will get sine term, so sine term. Now again we have to differentiate this function 2 pi x by lambda minus frequency into t, and then what I am going to get is 2 by lambda again, and so this will be 2 pi by lambda square. And if you look at this wave function, what you will find out is that this has minus a term and this has this term, which basically combined is equal to yxt, and you can simply write here yx in place of this, multiplied by 2 pi by lambda square with minus sign, so minus does not come in here, so minus sign. So, d2 yx by dx square is equal to minus 2 pi by lambda square yx. So, this is time independent differential equation of a wave, since we have taken t as a constant, So, this is applied to any kind of wave. This equation is applied to any kind of wave. It means it is applied to water waves, it will be applied to a sound wave, and also it is applied to light wave. Now, till this point we were not considering about, we are just considering the motion of a wave. Now, let us come to see how we can write a differential equation of a wave associated with electron, So, here the proposition made by de Broglie comes into picture. What he told, that de Broglie wave for a particle is made up of a superposition of infinitely large number of waves of this form, and for this kind of wave you have this differential equation. Now, only thing what we have done is, in place of y we are now writing psi x, where psi is a wave function, Okay. So, this is a wave function associated with an electron. Now, what next? So, at this point what we are talking is one dimensional movement of the wave. So, this is the equation for an electron when the wave associated with electron is moving in x direction. But suppose if wave is moving in 3-dimensional space, then this equation can be written like this. So, now differential, the double differential or second differential will be not only with respect to x, but it will also be with respect to y and with respect to z. So, you will write del a square by del x square plus del a square by del y square plus del a square by del z square in place of dA square by dx square, and now psi is a function of x, y, z. So, same equation just only written in 3 dimensions. And to make things short, you replace this sum of 3 second order derivative by del a square, and this combination of second partial derivative is known as Laplacian. So, this only simplifies the thing. So, now this is your equation of a wave associated with electron in 3 dimensions. Now, what Schrodinger did is he replaced this lambda by h by p. So, he was influenced by the hypothesis of de Broglie, where de Broglie predicted that lambda is equal to h by p. So, lambda associated with an electron is h by p. So, what can be done is just replace this lambda by h by p. So, let us think. So, for a particle, energy will be given by kinetic energy plus potential energy, which is half mv square plus v is your potential energy, and we know that the kinetic energy is also equal to p square by 2m. From that you can calculate what will be the value of p. P will be simply E p square will be, you see, p square will be E minus v into 2m, and so p is equal to 2m E minus v square root. And we know that from de Broglie equation, lambda of an electron will be given by h by p. So, lambda can be replaced by h by 2m E minus v square root of this. So, when you replace this lambda by this expression, what you will get is 2 pi by lambda square will be 8 pi square m E minus v by h square. So, Schrodinger took your equation of wave and then he plugged in value of lambda, from de Broglie equation, and what he got is well known Schrodinger equation, and that is your minus h square by 8 pi square m, this Laplacian operator into wave function plus potential energy into wave function will give you energy into wave function, and this is well known Schrodinger equation. So, Schrodinger utilized the concept given by de Broglie to derive a equation which can tell you about trajectory of electron. Good thing about this equation is, if you solve this equation, you can get the wave function and energy associated with the different quantized levels, energy associated with different quantized energy level. This is your Schrodinger equation, and this whole term, so this is your kinetic energy term, this is potential energy term, and that is given by operator H, I will just talk about operator H or operators, what are operators, but this is your equation which is known as S psi is equal to E psi. In this equation what you are doing is you are applying Hamiltonian operator which is given by this symbol and getting your energy value, getting the energy value. So, when you apply the Hamiltonian operator on the wave function, what you are going to get is energy multiplied by the wave function, energy multiplied by the wave function. Now, there are two very important things which comes into this Schrodinger equation. One is wave function and another is operator, and in this case Hamiltonian operator. So, now let us discuss what are these parameters. So, wave function, quantum mechanics acknowledges the wave particle duality of matter by supposing that rather than travelling along a definite path, a particle is distributed through space like a wave. And the wave that in quantum mechanics replaces the classical concept of particle trajectory is known as wave function. So, basically wave function describes the trajectory of your microscopic particles. So, a wave function in quantum mechanics describes the quantum state of an isolated system of one or more particles. There is one wave function containing all the information about the entire system, not a separate wave function for each particle in the system. That is very important part. Just by knowing the wave function, you can tell all the information about the system, all the information about the system. So, what is momentum, what is position, what is your kinetic energy, what is total energy. These things, the information about these parameters is contained in the wave function. Now, let us go and try to understand wave function a bit. Let us go and try to discuss quantum mechanics. So, quantum mechanics is described by different postulates. Different postulate. What I mean by postulate is there are certain rules have been given. There are certain rules have been given, and you take it as face value, and what it has been seen is that if you accept the postulates of quantum mechanics, then the information about a microscopic particle, information of a microscopic particle can be obtained. So, first postulate is the state of a quantum mechanical system is completely specified by a wave function, which depends on the coordinates of a particle and time t. So, I have already talked to you that psi is a wave function of x, y, z and t. So, this is for one particle system. For two particle system, the wave function will be function of position of the first particle, position of the second particle and time. So, wave function will be a function of x1, y1, z1, x2, y2, z2 and time t. Wave function contains all the information about a system, and wave function is similar to classical trajectory in Newtonian mechanics. Wave function tells you about trajectory in the quantum mechanics. What is the physical significance? Physical significance is that you can get you can find probability of particle in a or around a particular point x, by using this equation. So, probability is given by your psi star into psi into d tau. Psi star into psi is known as probability density. When it is multiplied by volume element and you integrate it, you will get probability of finding an electron in a particular region or in d tau region. So, psi star psi tells you about probability density, and that is synonymous to amplitude square, which is proportional to intensity. And now you think of that what happens if volume element is small. Finding of an electron in a small volume element will be smaller. So, suppose in this room electron can be anywhere, and suppose you choose a very small space in this room, then probability of finding electron in this volume element will be very small, and in comparison to this whole room, and so probability is proportional to d tau. D tau is big, then probability will be big, and that is why PR is proportional to d tau. PR is proportional to d tau. PR is also proportional to psi star psi, which is probability density, and I explained that by giving you or by giving an analogy to intensity dependence on amplitude. So, there are a few things which is needed. Your PR must be greater than equal to 0. Here sign of wave function has no direct physical significance. The positive and negative region of this wave function both correspond to same probability distribution. The second thing is that if you integrate psi star psi d tau over all space, it should be equal to 1, and that is not a very difficult thing to understand, because probability of being an electron from minus infinity to plus infinity is going to be 1, since probability of finding the particle in the inverse is 1, and that is what psi should follow. So, there are certain rules for a acceptable wave function, and that is based on the real things. Wave function and its first derivative must be finite, or the wave function must be single valued. What does that mean? It means for any given value of x and t, psi, a wave function must have unique value. And why this condition? Because this is way of guaranteeing that there is only a single value of probability of the system being in a given state, and that is quite logical. The second thing is wave function must be square integratable. So, what does that mean is the integral of psi square over all space must be finite. What we are telling by this is, it is also logically valid, because what we are trying to say by saying that wave function must be square integrable is that the probability density must integrate over all space to give a value of 1, and which is not possible if the integral of psi square is infinite. And this also gives you one very important consequence, that psi must tends to 0 for infinite distance. The next criteria for acceptable wave function is that wave function must be continuous. A rapid change would mean that the derivative of function was very large, is very large. In the limit of a step function, this would imply an infinite derivative. Later we will find out that momentum of system is calculated using momentum operator, which is first order derivative, and if there is a rapid change, it means the derivative of the function will be very large. It means infinite momentum, which is not possible in a physically realistic system. So, all first order derivative of the wave function must be continuous. Following the same reasoning as we did in the last criteria, a discontinuous first derivative would imply an infinite second derivative, and generally energy of the system is calculated using second derivative. So, discontinuous first derivative will mean an infinite energy, again which is not physically realistic. So, if you look at these wave functions, this wave function is not acceptable, since at this finite value of x you will have 3 different values of y, of psi x. So, it is the wave function is not a single valued function. Now, the second one is also not accepted because it is a discontinuous wave function. Third again is not acceptable, and fourth is also not acceptable because you see there is a very sharp change in the wave function at this particular position of x. So, these wave functions are not acceptable. Now, let us think about these 4 different kind of functions: exponential minus x from 0 to infinity, exponential minus x minus infinity to infinity, sin x by x, and sin inverse x. So, in exponential x, this is exponential minus x. So, you can see the plot between exponential minus x as a function of x. Now, you see here this wave function is acceptable if we take from 0 to infinity. If we remain in the region 0 to infinity, but this is not acceptable in a region when you go from 0 to minus infinity. Sin x by x, this is an acceptable wave function. It meets all the criteria for an acceptable wave function. Sin inverse x, this is the plot of sin inverse x versus x. This is a plot of sin inverse x versus x. Now, you can see that x will be 0 at y is equal to 0, y is equal to pi, y is equal to 2 pi, and so on. So, this wave function is not a single valued function, and so it cannot be a acceptable wave function. It cannot be a acceptable wave function. Now, the postulate 2 tells you for every physical property observables in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. So, there are 3 important parts of this postulate. One is observable, what we mean by observable, and then the second is operator, third is your linear, and fourth is Hermitian. So, we will go to these 4 of them one by one and try to understand what we mean by this. So, let us discuss about your observables. What are observables? Observables are anything which is a function of position or and momentum. For example, position is a function of x, momentum which is function of px, kinetic energy which is a function of p, momentum, your potential energy which is a function of position, and total energy which is a function of position and momentum. So, these are the observables. What are operators? Operator is a rule that transforms a given function into another function. So, if you apply operator O on a function f x, it will give you another function which is your g x. So, operator transforms a given function into another function. So, here operator O is converting a function f x into another function g x, another function g x. Now, let us understand by some examples. So, suppose I have a operator d by dx. When I apply that on function x square, we will get another function 2x. So, d by dx is x square, d by dx x square is equal to 2x. So, this is first function. When you apply this operator d by dx, it will give another function which is equal to 2x. Similarly, when we apply operator d square by dx square on 4x square, what we will get? We will get first d by dx 8x, and then this will give you 8. This will give you 8. So, when we apply this operator double differential operator on the function 4x square, we are going to get 8. Similar kind of operator you can see here, and you can practice what you will get when you apply these operators on these functions. This is about operator part. What is a linear operator? A linear operator has the following property. If I take a combination of two function f1 and f2, and if I apply a linear operator, you take that value, and then what you do, that apply this linear operator to function f1 and f2 separately, then the two values must be equal. Two values must be equal. Now, you will say that it should be equal for every operator. No, it is not like that. For example, suppose you have a square root operator, Okay. So, a square root operator, for example, this one, f1 plus f2 will not be equal to a square root of f1 plus a square root of f2, So, this condition does not hold true for every operator, but this will be true for a differential operator. This will be true for a differential operator. So, differential operator is a linear operator. So, when operator is applied to a combination of two different functions and it is equal to when sum of when you apply operators separately to these two functions, then you have a linear operator. The second condition, which also should be maintained, is when you apply this operator to a function multiplied by a constant, you must get constant multiplied by operator of that function, constant multiplied by operator of that function. So, two conditions: you apply operator to the combination of two wave functions if it is equal to operator of function f1 plus operator of function f2, and the second is when operator is applied to a constant multiplied by a function that should be equal to constant multiplied by operator of this function. So, we discussed observables, we discussed your operator, I discussed your linear operator. So, now we will go to Hermitian operator, but before that I will tell you to look at these 4 questions or to look at these operators and tell whether these operators are linear or not. You should check whether derivative is a linear operator, where integral is a linear operator, where log is a linear operator, where a square root is a linear operator. I just discussed about a square root, it is not a linear operator. So, since now time is over, so I will not be discussing Hermitian operator, I will discuss in the next class. So, thank you for listening, and go to last slide. I would like to acknowledge these books which I am referring to, and thank you very much for listening. See you in the next lecture. Thank you. Bye.